introduce the concept of RC circuits, so resistor capacitor circuits. We've already seen kind of arrays of capacitors. We've talked about how capacitors charge and discharge, but we haven't really analyzed what happens over time. We've basically said, oh yeah, they start out uncharged, they end charged, we know that current can flow, but how would we describe that current over time or the amount of charge over time when you're not looking at that equilibrium state kind of at the end? So what we have kind of assumed is that your capacitor goes from uncharged to charged. What that would look like is uncharged and charged. So you'd have like uncharged, and then at some instant in time, now it's charged. And that's not what happens, because it takes time for that charge to develop. So what happens is our charge starts out at 0, and then your capacitor actually gains charge very quickly at the start, and then the rate at which it finds more charge to develop gets smaller and smaller and smaller. And actually, there is an asymptote here. And that asymptote means that your capacitor can never actually fully charge. That only can you consider the capacitor fully charged if time has approached infinity. In reality, we're going to get some point where basically the charge is changing so slowly that it might as well assume to be fully charged. And to our measuring devices, because they don't have an infinite decimal of precision, we can assume that it is fully charged when the current, say, in the circuit stops changing. The charging speed, the rate at which it charges, is dependent on the capacitance and on the resistance between the battery and the capacitor. So we are going to derive equations that kind of show why this is true, but those are going to be the key factors. So if we have a larger capacitance, we're actually going to charge slower because it's going to take a long time for it to actually become fully charged. If we have a large resistance, the current's not going to flow very quickly, so the charge isn't going to build up very quickly. And then what we can do is we can derive equations for basically the charge on that capacitor as a function of time. And then remember that current is the rate of change of charge over time, and voltage is current times resistance. So we can develop kind of a series of equations that can describe the current, charge, and voltage across the capacitor and any other component in the circuit at any point during the charging process, and then eventually during the discharge process. So as you saw, there's a derivative in there, and we are going to see that charging and discharging are time dependent, and we are going to have to use calculus in order to find those functions. So just a note on Kirchhoff's loop rule with capacitors. So we've already seen how to use Kirchhoff's loop rule with resistors and our EMF sources, our power supplies, batteries, and so forth. Now we can add on our capacitors. So what we can see is that the traditional way we look at capacitors is on this table is actually going to be kind of the opposite. When we looked at resistors and EMF sources, the way we normally think about resistors and EMFs is on the left. The normal way we kind of think about capacitors just happen to be on the right of this table. So when you have your capacitor and you think about current flowing, while we are charging, what's going to happen is, you're going to have some power supply over here that is going to be at a higher potential, and that's going to cause a positive Q to start developing on the side of the capacitor that's closest to that. If the travel direction for your loop is going from that same direction that your conventional current would flow into that capacitor to charge it, that is going to be when your delta VC is equal to negative Q over C. And you're going to have a voltage drop across that capacitor that is dependent on the charge and the capacitance. Okay, so that is going to be your equation. So that's kind of like here with your resistor, where you're experiencing a voltage drop. Now, if your travel direction for your loop is actually going from lower to higher potential, then what happens is that capacitor is actually treating it like it's discharging, and it's actually acting as the voltage source, and so you're going to end up with positive Q over C. So this is acting more like a discharge. It doesn't have to be discharging in order to actually have this equation, but for it to show up as positive inside of your loop rule, you're going from the lower side to the higher side, the negative side to the positive side with your loop. When your loop is going from higher to lower or positive to negative, we're going to have that voltage drop. Okay, so this is the one that I tend to remember. These are the ones that I tend to remember with the EMF and the resistor. And then if it's not that, if it's doing the opposite, then it's going to have the opposite sign. So we're going to look at the simplest RC circuit that we have, which is a single resistor and capacitor in series. Now realize, if your resistor and your capacitor in parallel, the circuit will behave completely different. If there are multiple resistors, multiple capacitors in different arrangements, the circuit will behave differently. But this will allow us to kind of understand how to write these rules and equations. Another thing you're going to see a lot with RC circuits is there's going to be switches involved, and those switches may actually create like alternate paths. So you may see circuits that have like different resistors or different capacitors in them, and it says, okay, well, if the switch is in this first position, say position A, then your current's going to flow through here. And then they'll be like, okay, well, now we move the switch to position B, now the current's going to flow through here. Or there may be multiple positions for those. Okay, so that's something else that we're going to start seeing. So in this particular circuit, we're going to start with the switch open so that no current is flowing. We are also going to assume that our capacitor starts off uncharged. Our voltage source is E, so it's an ideal voltage source. That's the EMF, okay, so there's no internal resistance. And we're going to assume that our wires have no resistance. So nice ideal situation. So as long as that switch is open, it's impossible for there to be any current to flow. When you close the switch, the current is going to start to flow. Now, the most important thing to realize about an uncharged capacitor is that it's going to behave differently depending on whether it's charged or uncharged. So if you recall, the voltage drop, or the definition of capacitance is Q over delta V. So if we rearrange that and solve for delta V is going to equal Q over C. So you saw that in that chart. That's where that was coming from. Okay, when we look at the chart on the previous slide, Q over C, that's coming from our definition here of the potential of a capacitor. So with this, if my charge is 0, then the voltage drop across my capacitor is 0. Well, a wire with no resistance also has a voltage drop of 0. So an uncharged capacitor has delta V equal to 0. So that's going to be really, really important. So at T equals 0, current will start to flow, but the capacitor starts off uncharged and it starts off with no potential difference. So when you look at the current, when you make a note of this, I would say that IC is equal to 0, where this is the current in the branch containing a fully charged capacitor. Because if you have a more complex circuit, there may be multiple branches, and only the branch containing a fully charged capacitor is 0. If In this case, you have no current flowing through the branch with the capacitor. Any resistor is going to have its voltage equal to 0, because voltage of the resistor is I times R. So if there's no current flowing through that resistor, then the voltage for that resistor is also 0. In this simple series circuit, RQ is going to equal to C times E. That's also coming back up to this equation and solving. E minus Q over C is equal to 0. If you solve for Q, Q is going to be C times E. Now that is true, and this is going to be our maximum charge if you have a simple series circuit. You can figure out the maximum charge in non-simple circuits, but you'll have to do the calculus first to figure that out. Or basically look at some of the limiting conditions and kind of figure out how that's going to work. So make sure you are using subscripts. You're using like VC for the voltage of the capacitor, VR for the voltage of the resistor, because they're not always going to be the same. Sometimes one is 0, the other is not 0, and so forth. It gets a little crazy. Subscripts are going to be super, super important. You're going to see that as we start working problems that involve more components, and you'll see those in the derivation packets. All right, so to do the calculus derivation, you have to choose an arbitrary time. So that is going to be some time that is not t equals 0 or t equals infinity. So some time between the capacitor being uncharged and the capacitor being charged. Our loop rule doesn't change, but we can't simplify it down. And then, like I showed you before, you sub in I is dq dt, and then this is our differential equation. So I'm going to show you how to solve this differential equation. So one of the first things that I do when I'm solving this equation is I absolutely hate having a lot of fractions. It gets very, very complicated. So we're going to need to get some common denominators and things to do some of the work. So the first thing that I'm going to do is I am going to actually combine this term right here using a common denominator. So I'm going to multiply the E by C over C. So I get CE over C minus Q over C. And I'm going to add this term over here to the other side. The reason I'm going to add that to the other side is it's got the dt in it, and I like the dt to be by itself. So I'm going to have that equal R dq over dt. So I'm going to move the dq dt term to the other side because I want my dt to be kind of on its own. Move that over there for right now, and I'm getting a common denominator with what's left. So that's going to give me CE minus Q over C is equal to R dq over dt. So now what I have here is my equation is a little simpler because I don't have a bunch of fractions and stuff. I just got a couple here. You might not see that has gotten simpler, but it actually has gotten simpler. My next step is to separate variables. And if I did not do this step, I would not be able to separate variables. So I need to get that common denominator to separate the variables. So I'm going to get all the Q terms on one side and anything that doesn't involve a Q on its own. So I'm going to have to do something funky. I need my dq to be on top, and I also need a dt to be on top. So I'm going to multiply the dt to the other on both sides. So that's going to cancel it from here. And then I'm going to divide the CE minus Q to the other side. So that'll cancel that one over here. So, and then I'm going to also divide my R. So I'm trying to get that anything that is not a Q over to the other side. So what this ends up giving me is it gives me dt over RC is equal to dq over CE minus Q. All right, so the next step I'm going to do is not necessary for the calculus, but it's going to make my equation look like how I need it to look to understand the physics a little better. So strictly from a calculus standpoint, this step is also not necessary, but from a physics standpoint, to get an equation that has more meaning, this is the step that we're going to do. So what I'm going to do is I'm going to get rid of that negative in the denominator in front of my q by multiplying top and bottom by -1. So distributing that -1 is going to give me a negative CE and a positive Q. So I'm going to rewrite that denominator as Q minus CE. And then on top, I'm also going to have a negative for that DQ, but I'm actually going to multiply that negative over to the other side. So I'm going to get negative DT over RC. And there's a very, very particular reason why I'm going to do this, and that's to make the physics equation make sense. So that is now fully separated, and I am ready to integrate. So when you start looking at this equation that we've written here in green, you are going to compare it to the formula sheet. And one of the integrals that we give you on the formula sheet is the general equation that you can use to find the natural log function. So in this case, x is going to be our q when you compare those. A, in our case, is 1, and c is negative CE. That's our capital C capacitance. That's a little confusing right there. So when I go to integrate, I'm going to integrate from 0 to q of t. I'm going to q of t and not just q because I'm trying to find the charge as a function of time. So that q of t represents any arbitrary time from t equals 0 to q whenever it's fully charged. And then on the left, I'm going from some time 0 to time t. So whatever that t is, that matches that q. If I wanted to find like the final charge, I could actually integrate to infinity on the time and to q max on the charge, and that would actually give me my maximum charge if you wanted to do that integral instead. But that's not what we're going to do because we're doing it for any point in time. So we're going to apply on the right side this equation. So we get 1 over a, so that's just going to be 1 over 1, natural log of a times x, which is just q, plus c, which is our negative CE. So really what that is, what's kind of nice, is if we don't have an a, it's just our denominator. So like I said, it's a little bit easier to use than having to do anything really complicated. Plus, it makes it look like how we want it to. So really, this is just natural log of our denominator, q minus CE. That's really all that is, okay? That's how you use that function. And then we're going to evaluate that from 0 to q of t. Remember, this is a step you always show. On the left side, when we integrate dt, we're just going to get t for that. And then we're going to leave our constants, which is negative over RC. And that is going to be evaluated from 0 to t. I know some of you probably, if you want to, do this like perfectly, you'd have to have like a dt prime. That would be a t prime, and then you sub in a t. It's convention, different ways to kind of show things a little bit more proper. So you can do that. Either way, doesn't matter. So then what happens is you get negative t over RC minus 0 over RC. And then over on the right side, we get ln absolute value of q of t minus CE minus ln absolute value of 0 minus CE. One of the biggest mistakes that I see people do when they're solving this is they skip the point where they actually show subbing in the zeros. A lot of people I see when you solve your problems will just say, oh, that's just going to be T over RC, and that's 0. I'm not even going to show it. And you might assume that this second term is 0, but it's not, because only the Q is 0. So you have to be careful. So on the left, we get negative T over RC. And on the right, we actually get ln of Q of T minus CE minus the natural log of negative CE. Another thing that you need to avoid, do not take the absolute value to get rid of the negative. Don't do it. We need that negative there later on. It will mess you up and get you the wrong answer. We are then going to use our rule for combining natural logs. Because those natural logs are being subtracted, you can divide them in one term. So on the left, I'm still going to have negative T over RC. And that's going to equal the natural log of Q of T minus CE over negative CE. Now, remember a little bit earlier that I told you that CE was special? Q max for a simple series circuit is actually CE. So our Q of T is always less than or equal to CE. So when you look at this natural log, you can only remove the absolute value if your whole term is positive. So this is why you can't take that absolute value earlier, because Q of T minus CE will always be a negative term or it will be 0. So you have a negative divided by a negative. This whole term is always positive or 0, which means you can take away the absolute value. If you had taken this absolute value earlier and you had that denominator as positive, you would not be able to remove that absolute value and you will end up with the wrong answer. So that is 2 reasons why you need to make sure that you don't do that. So we're going to pick up here, back up at the top. I have my equation that I derived. I've removed the absolute value from within the natural log because that term is always positive. And I've recognized the significance of C times E because it is Q max for this case. Now, what's really interesting is if this is not a simple series circuit, you will get a function that looks very similar to it, and your Q max is still going to be related to CE. It just might not be exactly CE. It might have some other stuff in it. And if you have a really complicated circuit, this left side is always going to look very similar, but it might have some slight differences in it. But it's always going to involve R and C. So my next step is to find Q of T. In order to do that, I have to get it out of that natural log. So I'm going to raise on both sides E to both sides of that to get rid of that natural log. So on the left, I get E to the negative T over RC is equal to Q of T minus CE over minus CE. And then you can multiply by that denominator. So I get minus CE, E to the negative T over RC is equal to Q of T minus CE. I'm going to add that other CE to the other side to get Q of T by itself. I end up with CE minus CE, E to the negative T over RC is equal to Q of T. And then by convention, we combine those CE terms, pull out the CE. So I get CE, actually I'm going to write Q of T is equal to CE times 1 minus E to the negative T over RC. And that is the equation for the charge over time of a simple series RC circuit. So, couple things about this. We have this term in front, no, even if it's not CE, is going to be Q max. And then this guy right here has a special name. This guy is the time constant. and it gets a special variable. It's tau. That is the Greek letter tau. It's the same symbol we use for torque, which is kind of annoying. So that time constant, oh, kind of got covered here, basically is a measure of how fast the capacitor is going to charge and discharge. So you can see that our tau is equal to RC. So the larger your resistance, the larger your time constant is. The larger the capacitance, the larger the time constant is. So if your resistance in the circuit is larger and your capacitance is larger, it's going to take longer to charge. The resistance is a factor because it's affecting the rate at which the charge can transfer. So more resistance, smaller currents, therefore it takes longer for the charges to move. Larger capacitance, if I have a big capacitor and I need to fill it all up, it's going to take a lot longer to fill up than a smaller capacitor. Okay, so the bigger capacitance, the longer it's going to take to charge. Now, the other thing to recognize is the shape of this graph is a 1 minus e to the negative x type thing. So that is going to end up looking like this guy, Q and T, and there is going to be an asymptote, and that asymptote is going to be Q max. So you're never actually going to reach Q max, but if you look, if you take T go to the infinity, then you get negative e to the negative infinity. Well, e to the negative infinity goes to 0. So this whole term goes to 0. And then 1 minus 0 is just 1. And then that gives you that Q of T is just equal to Q max as T approaches infinity. The other thing I can see with this is I can check what happens at T equals 0. Well, at T equals 0, e to the 0 is just 1. So e to the 0 is 1. 1 minus 1 is 0. CE times 0 is just 0. So Q of T is equal to 0 at T equals 0. So the assumptions that I told you about apply to this equation. So let's say that you are working a problem on a test and you get stuck. If you're not sure, and I'm asking you what's going on as T approaches infinity, you don't necessarily have to go through the whole derivation. You can think about, okay, at T goes to infinity, there's not going to be a current flowing through the circuit that involves the capacitor, so let's see what we can do with that. You can also, if I give you an equation, you can figure out what Q max is, because Q max is going to be the limit as T approaches infinity. You can figure out what was the initial charge of the capacitor. It doesn't have to be 0. You can work this problem with it starting out charged. And you can go from there, and you could actually then say, okay, if I plug in T equals 0, did this thing actually start off with a charge? In this case, it wouldn't, obviously, because that was the assumptions that we made to derive it. But you can look at those equations. So what if you wanted to find the current? So that was charge as a function of time. Well, to find current, our current is dq dt. So I'm going to take the time derivative of that Q of T equation, which was CE times 1 minus e to the negative T over RC. Well, the CE is a constant, so it can come out in front. And then I have to take the derivative of what's left on the inside. Well, the derivative of a constant is just 0, so that first term goes away. So, and then I do have to do a chain rule. So the derivative of an exponential function is just the same thing. So I'm going to have the minus e to the negative t over rc, but then I have to multiply by the derivative of the inside. Well, the derivative of what's inside that exponent is going to be the derivative of minus t over rc. So that is going to be minus 1 over rc. So those negatives are going to cancel. here, and here. And then I can simplify that. Actually, that's a C on the, that's all multiplication or division. So the C on the bottom cancels the C on the bottom there. And what I get is E over R, e to the minus t over RC. And that is going to be my current as a function of time. So what would this graph look like? Well, this graph is an e to the minus x function, so that's just going to do this. And that is going to have an asymptote of 0. So what it tells me is over time, you are going to end up with a current that is 0, and it's going to start at e over r. And that's because if you go to infinity, so as t approaches infinity, e to the negative infinity is 0. So I is going to go to 0. So I of infinity is 0. If we look at what it is at the start, look at those initial conditions. If I plug in a 0, e to the 0 was 1. So I of t equals 0 is going to be e over r. Well, that e over r is significant. That's just Ohm's law. And that is our EMF. Because remember, we're dealing with a simple series circuit. And remember, when that capacitor is uncharged, it behaves like a wire with no resistance. So it's basically like the capacitor is not there. So the current in that circuit is just going to be E over R. So you're going to get your maximum current at t equals 0 because the capacitor has no voltage drop across it. So only the resistance is determining the current. So that's going to decrease over time. And then that RC time constant still appears. So what you end up getting when you charge the capacitor is your Q of t is going to be your Q final or your Q max, which for a simple RC circuit is going to be C times E, times 1 minus e to the negative t over RC. For the current, it's going to be E over R. That's your I max, okay, based on the resistor, the capacitor not having a potential difference across it, e to the minus t over RC. So you can go and do that. It's a little more complicated if you have more than just a simple series circuit. That's what the derivation packet takes you through. So here's some example plots with your initial voltage of your power supply being 10 volts, a resistor of 200 ohms, and a 1000 microfarad capacitor. That's a pretty big capacitor. Your RC would be 0.2 seconds, because if you take 200 ohms times 1000 microfarads, that's going to give you 0.2 seconds. You'd have to convert the microfarads to farads first. And so that's going to be your time constant. So where does that time constant show up? The time constant gives us a measure of 63% of the charging capacity. So in this case, when you look at this graph, that 63%, not 66%, not 2/3, it's a little less than 2/3. 63% fully charged is going to be your RC. Now, why that's significant is because we assume, since there's an asymptote, we assume that we are fully charged at 4 to 5 tau. So if we look at 1, that's 1 tau, 2 tau, 3 tau, 4 tau, and 5 tau, we assume that by the time we reach 5 tau, we are close enough to that asymptote to be considered constant. You can see 4 tau's almost there. It's a little bit of an underestimate on this scale. But definitely by the time you reach 5 tau. So if I've ever asked you a question about how long does it take for a capacitor to fully charge, it's true that it never actually fully charges, but we're asking for an estimate. So of how long that would be, and that's going to be, you could do either 4 or 5. You could do, so I could do 4 tau to 5 tau, and you'd calculate it, whatever your tau is. Okay. For that same here, when you look at this one, on the current, because that's actually a decreasing function, that tau is going to give you 37% of the current on going down on the other side. That's going to show us right here. There we go. Let's clean some of this off. So 37% of the maximum when you're going for a decreasing function. Okay, that's the significance of the time constant. You could also find the voltage across the capacitor as a function of time, and that's going to be Q over C. You could find Q of T over C. You could find the voltage across the resistor as a function of time, because that's going to be I of T times R. I ran out of room. I of T times R. So you could find the voltage across the resistor as a function of time, or the voltage across the capacitor as a function of time. Okay, so that's charging. What about discharging? Well, basically, in order to discharge, you can't have a power supply. So a lot of times they'll have the power supply kind of off on its own little switch. So they've actually just taken the power supply out. So sometimes what they'll do is they'll just have a switch that kind of goes from this position down to that position here. They'll say, okay, well, in position 1, your power supply is connected here like that, so you're charging with that switch closed. I guess they're technically and then there's no connection here. And they say, okay, now that the capacitor's been charged for a really long time, let's move the switch down into this position so that isolates the power supply. And now you have this fully charged capacitor that has all this potential energy stored in it. And you've got this resistor, and now you have a connection. So we are going to assume that our capacitor actually starts off fully charged when we go through and do the discharging. So while the switch is open, or it's in another position, in this case, you're not going to have current flowing. Or if the capacitor is fully charged and the battery is in there, you don't have any current flowing. And then you're going to make a change that's going to allow current to flow. This time, because you have that potential built up, your capacitor now acts as your power supply. It acts as your EMF. So you're going to have current going from the positive to the negative side of your capacitor. And that is what we're going to measure over time. Now that energy is getting converted to heat when it goes through that resistor. And so over time, your capacitor is going to fully discharge, and there will be no current going through the circuit. So this loop rule is a little bit simpler because you have Q over C minus IR. There are different ways for this to work. In this case, we've actually changed the direction of our loop. When we worked the charging, we assumed that our loop was going in this direction. So you can actually assume that. And if you do that, that will change kind of the way that you work the problem. Because in this case, if your current's going that way, you're going the wrong way through the capacitor, and so you would end up with a negative right here. This problem is going to handle that a little bit differently, because we've chosen our direction to go from negative to positive, and so we're going to have a little bit of an issue. Okay, really not an issue, but if you had changed the direction, this one would be negative and that one would be positive. Okay, so if you went that way. So just be aware of like the direction changes that you have. And that's because the current would actually be going the opposite direction of the loop. So they're defining the loop to be the same direction as the current flowing. So once again, at an arbitrary time, you would use your loop rule. You would sub in dq dt, but if you use this method, you actually have to plug in a negative dq dt because your rate of change is decreasing over time. I may do it slightly differently in the derivation packets. I may set it up with a loop so that you don't need to do the negative, because if you, like I said, if you keep your loop direction going this way, well, if you assume your current's going to flow that way, keep your loop direction that way, then that sine is going to take care of itself. But we're going to keep going through this way. For this one, you don't need to worry about it too much because the sign error will take care of itself if you do have it. So what ends up happening is you get that our I is inherently negative. So you put that negative in here and it switches to a positive, okay, because we're decreasing over time. So we tend to use that dq dt to represent the magnitude of the rate of change, and we add the negative in ourselves. So when we go to solve this one, it's actually not as bad. So we have q over c plus r dq dt is equal to 0. So we still need to separate. So I'm going to move the r dq dt to the other side, kind of like I did before. That's getting subtracted, though, in this case. And then I'm going to kind of cross-multiply this stuff out. So I want the dt to be on the other side. I want the negative, and I want the r to be on the other side. So I'm going to multiply by negative dt over r. And on this side, I want to multiply by 1 over q. Okay, so I don't want to do that across to the whole equation. And so then what that ends up giving me, it gives me on the left, it gives me negative dt over rc. And on the right, it just gives me dq over q. So I get very, very similar function. It's just the denominator is a little simpler. Then if we want to go through and solve that one, we just need to integrate on both sides. This one's a lot easier to handle because dq over q's, that's just our basic natural log. And we're going to go from q max to q of t, because we are starting off charged and we're going from 0 to t. So on the left side, we're going to get negative t over rc. On the right side, we're going to get the natural log of q. Evaluating from 0 to t, evaluated from q max to q of t. So that's one thing you have to really be careful of, is the limits on this one, because we're starting off charged. So on the left, that does end up being negative t over rc minus 0 over rc, so that term just goes to 0. And then we get the ln of absolute value of q of t minus ln absolute value of q max. We can then again combine those together. I get negative t over rc on the left is equal to natural log of q over t over q max. The absolute value is there, but you don't really need it because you can't have negative charge, so that's fine. And then to get q of t, you're going to have to do the exponential on both sides. So you get e the negative t over rc is equal to q of t over q max. So then you just multiply q max on both sides. And what we end up getting is we get q of t is equal to q max e to the negative t over rc. And what would have happened is if you had forgotten this negative right here, you would have ended up with a positive t over rc, and you would have recognized that that would have actually been exponential growth. And if it's discharging, the charge has to get smaller. So it's something you could have fixed. getting your negatives wrong on the charging would have been more complicated. You could have ended up with an incorrect function. So you do have to be careful, but you can kind of reason your way through some of it if you know you've made a mistake. So with our Q of t here, this graph is going to be exponential decay. So you're going to end up with Q of t. It's just going to be your decay function. You're going to start off at Q max, and you're going to go to 0 as t approaches infinity. And you can see that RC is still there, so that'll come into play. And then you could also, once again, find I through that branch. I of t is going to be dq dt. You could find VC is going to be Q of t over the capacitance. You could find VR is going to be I of t times R. Okay, so all the things we did charging, we can do discharging. So looking at the discharging a capacitor, this Q0 is whatever your starting charge was, which was our Q max from discharging, from charging. And then you got your I of t. This I0, when you look at that one's going to kind of depend on your values a little bit differently. So we could actually do that one. Let's go back and solve that. So if I wanted to find I of t is going to be dq dt, which is going to be ddt of Q max e to the negative t over RC. So your Q max will pull out in front, and then the derivative of an exponential is the same thing, plus a chain rule on the inside. So we're going to get Q max, negative Q max over RC. E to the negative t over RC. Now that negative is coming from a very particular reason, and that's coming because the currents actually switched directions from when it was charging. So that's really where that negative comes out, is that change in directions. Because going around that circuit initially, when it was charging, your current was going that way through the resistor and the capacitor, but when it discharges, it actually flips direction. So that's where that negative comes from. That's kind of what that means there. But in terms of the magnitude of the current, that magnitude of the current is going to be Q max over RC. But remember that our Q max, if we were fully charged before, was just C times E. So you're still just going to get that E over R for that, because you're going to have that simplified function there. So same kind of idea with your discharging capacitor. You're going to end up with your time constant being to reach 37% of its maximum value. Same with the current. So in this case, both the charge and the current are going to decrease over time to 0 as t approaches infinity. So here are some things that you can use. Don't memorize these equations straight up, because if you have a more complicated situation where maybe you have like a resistor here, and then you've got like a capacitor and a resistor in this branch, and maybe there's a resistor over here in that branch. If you have something like that, these equations will not strictly follow. The process that I just showed you will work, and you may have to do some additional loop rules to eliminate some unknowns, depending on whether you're fully charged or not fully charged, or you're kind of looking in between. But the derivation packet will walk you through how to work problems like that. So these are just starting to kind of recognize patterns. So while you're charging, your charge is going to increase towards an asymptote. Your voltage across your capacitor is going to increase towards an asymptote. Your voltage across your resistor is going to decrease towards 0. and just your current overall is going to decrease towards 0 in the branch with your capacitor. While you're discharging, your charge is going to decrease towards 0. Your voltage of your capacitor is going to decrease towards 0. Your voltage of your resistor is going to decrease towards 0. And your current is going to decrease towards 0. So don't necessarily memorize the functions because they're not going to be all strictly identical for the more complicated ones, but the patterns will be the same. Okay, you're going to get very similar patterns. So just a couple of hints for when you are working kind of the homework or more complicated problems. So your charge as a function of time is always going to equal C times your voltage as a function of time for a capacitor, or any other rearrangement of those variables. For resistors, Ohm's law always applies. Okay. So if you know the voltage across the resistor, you can find current. In some cases, the current through the capacitor and the current through the resistor are the same. Sometimes they're different if you have different branches, so you do have to be careful. And as long as you're dealing with a simple series, the current through the capacitor and the current through the resistor are identical. They will not necessarily be identical in some of these other cases, like for example that one that I just drew for you on the other slide. So if you have something like this, so say this one was R1, R2, and R3, I might define this one here as like IC. So when you do IC, IC is dq dt. You might have other currents. You might have IR1, or just I1, which is the current through resistor R1. You might have I3 as the current through resistor R3. I2 would equal IC because those are in the same branch. You would then have junction rules. So I'd have a junction rule right here that says that I1 is equal to IC plus I3. So whatever is happening kind of in this circuit over time might change, you know, based on what's going on. So at t equals 0, you know, this guy doesn't have any charge across it, so it's just behaving like a wire. So if I wanted to figure out the current at the start, I would do like a equivalent resistance for the circuit, basically ignoring the capacitor because that capacitor doesn't have a voltage drop. So it would behave just like a circuit that did not have a capacitor in it. You'd have to make assumptions, but you could do that. As t approaches infinity, there's going to be no current flowing through that one at all, so all of my current is going to flow through this outer branch. So we can then do just a simple series calculation to find the current in that branch. So when you start looking at these more complicated problems, when you're looking at t equals 0 and t equals infinity, we can use those assumptions for how a capacitor behaves to analyze the circuit. Where it starts getting more complicated is when you're looking for those Q of t functions. But once again, I do not expect you to be masters at calculus and differential equations. You will be expected to be able to set up equations. Sometimes you might be expected to solve an equation, but the whole test is not going to be differential equations. There will be questions that just expect you to analyze those limiting conditions at t equals 0 and t approaches infinity, so that way your score on this test is not fully dependent on your ability to do the complicated calculus. But you might still be expected to analyze those final and starting conditions, or maybe sketch graphs for what will happen over time without having to actually do the full calculus derivations.